Let's expand. Instead of just having two charges, we'll have more charges. And we'll want to calculate the electric field at different points in space. So the electric field net is just the vectorial sum of every electric field due to every charge you have. N is the total number of fields present at a location, and of course the direction of each electric field determines the sign used. Objective: find the net electric field at the origin for this charge configuration. Q1 at -8, Q2 at -2, Q3 at +4. And here's where we want to find the electric field. So the first thing you do, well, we've already done it. You mark the point on the sketch where the electric field is to be calculated. You then draw the electric fields acting at this point due to each charge separately. You then calculate each value of E1, E2, and E3, and if the field is pointing to the left, you give it a negative value, and if it's to the right, you give it a positive value. Then you sum them up with the pluses and minuses to find the total electric field at this point right here. Let's work a problem by putting in values for each charges. You can see here's Q1, here's Q2, and here's Q3. You've got the charge and the distance from the origin. There are many, many more of these problems in the classwork and homework, and I encourage you to work them. Step 1. Mark the point at which the electric field is to be calculated. Well, we've already done that. That's at point x equals 0. Step 2. Draw the electric fields acting on that point due to the three charges. Pull out the answer tab over here when you're ready to check your work. So pause the video if you'd like, and we'll be right back. Okay, we're back. So here's our electric fields. Let's look at them. At this point here, E3, it's a positive charge, so the electric field in that direction will be there. It also goes over there, it goes over there. It should have been a straight line. But we just care what's going on in the x-axis at this point. So E3 is generating an electric field in this direction. Here it is. E1, its electric field is going that way to the right and over here to the left. But again, we're just worried at this point where it will be. So that's to the right. So E1 is to the right. And just like E1, E2 is also going to the right. So here's our vector diagram. E1 and E2, their electric fields are to the right. The electric field for 3 is to the left. So this will get a negative value, and these two electric fields will get a positive value. Step 3, calculate E1, E2, and E3. Assign negative values to fields pointing to the left and positive values to fields pointing to the right. Take a couple seconds, pause the video if you'd like, and then pull out the answer tab to check your work. We're back. And here we go. Here's the equation we use for electric field. It's kq over r squared. For E1, which is due to Q1, we'll do it for the first guy. We know that's going to be positive because of our free body diagram. Here's K, here's the value of Q, and note that it is 8 marks away from 0, 8 meters. So here, we're calculating to this point in space. When we were doing electric forces, we always were calculating with the distance between charges. The difference here is we're looking for the electric field at this point. So that would be 8. Q2 would be 2, and Q3 would be 4. Notice E1 and E2, since they're pointing to the right, get positive values, and E3 gets a negative value, since that electric field is pointing to the left. Step 4, and the final step, sum the individual electric fields. Now make sure we deal with the vector nature of the total electric field. It's the individual electric fields which are also vectors. Now if you recall, or you can go back to the previous slide, E1 and E2 were positive. Here they are. E3 was negative. Now we pulled 10 to the third out here just to make the math a little clearer. You do the work and you find a net electric field and you get a positive value, 6.6 times 10 to the 3 newtons per coulomb. You have to specify a direction, and that's what you have here. It's to the right.